How about now? Okay. Okay. So thanks everyone for staying for the last few talks of the session. I'll be talking to you guys today about polarimetry. It's one cool trick that has moms everywhere mad. And it's really not used as much as it should be. It's probably something that you heard about while you were an undergraduate and have since completely forgotten about because most of us aren't using it in our research. The idea with polarimetry is really just that instead of thinking of light as just a scalar with intensity and wavelength information, that you think of it as a vector. So you still have that scalar information, but you also have information about your electric field oscillation. So is your electromagnetic wave having an electric field that oscillates up and down, side to side, in a corkscrew? That's polarimetry. In terms of observing a planet, I'll just do it here. In terms of observing a planet, what we're going to have, at least in an ideal case with a nice calm main sequence star, is unpolarized incident light coming from our star, and that's going to be scattering off a surface or off of an atmosphere, and that scattering or reflection is going to impart a trend in the way that the electric field oscillates. And so it's going to give us great contrast with our stars in those cases. I'm talking mostly about habitability today, but I wanted to touch on these other things that polarimetry has contributed to. Polarimetry has allowed us to constrain the albedo of HD 189-733b. The original claimed detection of polarized light from that planet is disputed, but those non-detections that dispute that have given us some physical constraints on the nature of the planet. More recently, observations in polarized light of the other hot Jupiter I have up there, WASP-18b, have allowed us to exclude certain cloud scenarios. Venus, of course, was famously observed in polarized light many times, and that allowed us to determine what the cloud species was dominant in that atmosphere, that was not a nice jungle planet right next door to us. In the case of Titan, polarimetry was used to give us the first indications that this was a cloudy, hazy world, and that the unusual photometry that we saw from that was not because we had snow all over the surface. That's a really interesting paper, by the way, if you look it up, it's on there, 1973. Very recently, we've had observations of stellar oblateness from rapidly rotating stars, even seen stars reflecting each other's light in polarized light. And we've had a lot of characterization of the interstellar medium, which is a really vital component to studies of exoplanets in polarized light. That's something that we need to take into account. Oh, is it? Ah, thanks. Okay, that sounds better. Yeah. All right. So as we have a planet that's moving through its phases around its star, we're going to see these key features come up in polarized light, coming from glint off an ocean if it has that, from rainbow, from other optical effects from clouds, and from Rayleigh scattering. And depending on what wavelengths we're looking at, different features will be dominant. So that allows us to characterize the exoplanets around their star. There's also some stuff that you can do as far as biosignatures, looking for chiral molecules, but I'm not really going to talk about that today, but I just wanted to leave it up to remind people to look it up. So one of the strengths of this, as I have touched on before, is that you can naturally know the star. If it's a calm star, you're going to create natural contrast with it, so you don't necessarily need to use something like a coronagraph. You don't necessarily need your planet to be transiting the star for you to be able to characterize it. Another benefit is that you can derive orbital parameters, even for planets that do not transit their star. Your inclination is going to change the shape of your polarized light curve, not just the intensity, but the shape of your polarized light curve. So that can be figured out using this method. Polarized light really lends itself to confirming the presence of clouds as well, and possibly to characterizing them if you can get enough data for that. So I'm going to show you a few models. Most of these models are going to be based on chemically evolved models from Andrew Lankowski's 2018 paper. So he was looking at the TRAPPIST-1 system and the kind of archetype planets that we might find there. So in these graphs that I'm going to show you in a little bit, we're going to be taking a few of these archetypes and comparing them to each other maybe including things like varying types of clouds and adding cloud cases. We're not going to talk about surfaces in too much detail. But the question was, if we have this information from the scalar components, things like the albedo of these different surfaces and the behavior in scalar light of atmospheres and of different types of clouds, what more can we know by looking at this in polarized light? So we have that for comparison in scalar light. We also have very different behavior of surfaces in polarized light, different surfaces polarize light in different ways. And even different types of ices can polarize light in slightly different ways, which could be vital in the far future for characterizing some types of exoplanets, but is immediately useful for characterizing the icy moons in our own solar system. For the plots I'm about to show you, this is just a dummy plot. I just wanted to point out that the x-axis is typically going to be just half of an orbit, so we're going from full phase to new phase. The y-axis is polarization in parts per million, so that's telling us the size of the signal. Current polarimeters are sensitive to about 1 part per million. And then at the top, I've marked some, and with the dashed lines, I've marked some key features to look for. I just want to point out that the maximum polarization is not necessarily the same as where we find the maximum signal. We need to combine the polarization in some cases with the amount of light that we're getting reflected off the planet. And if we're looking at a rainbow, that might shift depending on the species producing the rainbow and the wavelength that we're looking at. So our first point to examine here with one of the TRAPPIST cases is that polarizing features have distinct shapes. And of course, their dominance varies with wavelength. As you might expect, the Rayleigh scattering will be very strong if you're looking at blue wavelengths. And if you can start moving towards redder wavelengths, if you had a planet that had ocean glint, that would be a strong polarizing feature, and that would start to pop out as you look towards redder and redder wavelengths. If we have a planet that has a cloud present, we get these very distinct rainbow features. These are very clear features to see in polarized light. The strength of the rainbow compared to the other features like the Rayleigh scattering will depend on the cloud height. If you're very interested in how to determine your cloud height and kind of disentangle that from molecular abundances, I would highly recommend looking at that paper from Thomas Fauché, from 2017. It's a really brilliant paper, but I can't get into that right now. Right, and so even in cases like this, where we have an atmosphere that is maybe very strongly Rayleigh scattering and we're masking that weaker rainbow signal from a different species in the cloud, if we're moving towards red wavelengths, we're starting to be able to pick out the difference in those curves, the one that has the cloud present and the one that does not. So different scenarios of cloudy atmospheres do seem to be distinguishable. Just looking at these different TRAPPIST archetypes, you can tell them apart from one another. And of course, they are going to change in wavelength in particular and predictable ways. So this is suggesting that this might be a useful technique to tell different kind of basic anticipated planet archetypes apart. And I should point out that I'm kind of simplifying things here. I'm showing you the total polarization. In reality, we're normally looking at Stokes parameters. We have a little bit more information than the last few plots that I've shown you. So we're looking at Stokes Q and U, and we're getting positive and negative values that also behave in particular ways depending on your rainbow behavior and your scattering surface if you're looking at a surface. If the values on the y-axis have been worrying you after I told you we can currently detect down to around 1 part per million, you might consider looking at sub-Neptunes, mini-Neptunes. So GJ1214b, depending on its cloud species dominant in the upper atmosphere and the size of the particles, can produce optical effects that would be near current detection limits with contemporary polarimeters. So we're getting very close to that 1 part per million level in some of these scenarios. So with a part per million precision polarimeter, which is what we currently have, and several hours of observation, which is pretty typical of an aperture polarimeter observing these days. If we were looking for one of these 1 to 10 part per million signals from a planet, we could do that currently, just with what we have right now, with a 4-meter class telescope if we're looking at a star like HT 189. If we're looking at a star like Proxima Cen in R band, we would want to use an 8-meter telescope, Proxima Cen in B band, if we want to get some comparison in the different wavelengths and start to tell these features more clearly apart. We would need to use a 30-meter telescope. So basically, right now, if there was a hot mini Neptune in Proxima Cen, or something larger and hotter than that, we should be able to detect it, or almost be able to detect it, with a dedicated program. If we wanted to observe a dimmer star, of course, we just need to stare longer or use an even bigger telescope. If we want to be looking for planets in polarized light that are in the habitable zone, this would require that we improve our polarimeter design to some degree. So I tend to kind of summarize polarimetry by saying that although the nature of polarimetry reduces the throughput of your photons, it improves contrast and certainty. So we really need to be thinking about the scenarios in which this is a useful technique, and whether or not we want to be building our telescopes and our instruments for this sort of thing, and if so, what particular things we want to be looking for, because it is certainly useful in some cases, particularly dealing with clouds and things that are not transiting. We need to continue to characterize noise, particularly from stellar activity in cool stars, especially if we want to keep looking at M dwarfs. To overcome issues with throughput, to some degree, we can use things like dedicated stares and thoughtful observations, being a little more particular than maybe we've been in the past about which planets we're looking at. And to overcome noise, we can consider things like simultaneous observations that will help us characterize things like stellar activity to help us characterize that noise, and also improving technology, which sounds like a kind of assy, really easy thing to say and hard thing to do. But I just want to point out that HIPPY, the most sensitive polarimeter in the world right now for visible wavelengths, is built from 3D printed components and optical and lab materials that you can get out of a lab catalog. It's very inexpensive. It's very reproducible. And there are great ideas out there about how to improve the noise, the throughput, and the abilities of polarimeters that people have that could maybe be funded. I don't have a particular idea, just to be clear. So I just want to end on this note of pointing out that many upcoming space telescopes and ground-based telescopes have, or are considering having, or are definitely planning to have polarimeters. LUVOIR, Origin Space Telescope, the TMT, the EELT, WFIRST, all have plans for polarimeters, or are considering plans for polarimeters. We need to think really hard over what wavelengths those polarimeters will cover. For example, LUVOIR will only be in the UV, and Origins would, of course, be in infrared. And the kind of science that we would be able to do with that. We also need to think about architecture and whether it's useful for the kind of science that we want to do for us to have our polarimeters in front of our coronagraphs or after them, because that's going to also determine, obviously, the type of science that we could be doing. And with that, I'll open it to questions.
I wanted to ask a clarifying question.
Yes.
So are you assuming, like when you're talking about the clouds and the various surfaces, that it's like it covers the entire planet? Because you have to look at disk integrated, right? So then you're really combining.
Yeah.
Everything?
Yeah. So these are disk integrated signals for planets that have a uniform coverage of whatever it is that I put in there. So they can have a different grounds and a different, different layers of clouds, but it's over the entire planet. The output from V-star, which is the modeling code that I use, actually does produce a 3D output. So it's in the works, I guess. I don't know how fast it'll come along, but it's in the works to be able to produce or be able to use a 3D input to like improve the the swath of things that we could be exploring with V-star.
Thanks.
Yeah.
Questions? RJ.
Hi, RJ from Oxford. At the beginning, you mentioned chiral molecules, and then you said you weren't going to talk about it anymore, but I wanted to ask so do chiral molecules produce like a noticeable polarization signal in spectroscopy?
Yeah, so chiral molecules can impart circularly polarized light. That's really too weak of a signal for any time in the near future to be doing that with exoplanets, most likely. But it's something that's really useful and interesting for astrobiology studies in our own solar system. You could potentially be doing this just with like a Europa lander or something like that. Yeah.
Tad up front. Oh.
Hello.
Yeah.
Oh, that was a really interesting talk. Tad Kamasic, UChicago. So it seemed like you needed like phase resolved observations to get information about, say, like clouds or something in the atmosphere. Do you always need like a full half orbit phase curve, or is there like shorter term observations that can tell you something similar?
You could, if you have some idea of what you want to look for or what you could anticipate from a planet, which I mean, you can just sometimes do from physics, knowing the size of it and what sort of, clouds you might expect where. You can just kind of sample around where you might expect, say, a rainbow and see if you do see the peak in the rainbow exactly where you predict. If you think that there's water clouds at the top of the atmosphere, does that arise at the right spot for the cloud height that you expect? You can really narrow this down. So you can just do a lot of sampling at a particular point if that's something that you're looking for. If you're trying to do something like constrain orbital parameters or something like that, that's depending a lot more on like the general shape of the curve, and you would want really good sampling throughout.
If there are no additional questions, let's thank Kim.